Welcome to the physics class for December the 14th. Before we get started, a couple brief announcements here. First off, don't forget that the test rework is due this coming Friday at midnight. And when I looked on there this morning, I saw that not one of you has done it yet. You've had it for a week. You could have done it. Don't leave it for the last minute, guys. The test rework is an assignment worth 24 points, which is more than half. It's almost 2.5 times what a regular homework assignment is worth. So make sure you do it and do it on time. Speaking of tests, you can expect that we will take another test before the term ends. That's a guarantee. We won't do it this week, obviously, and then next week is winter break. So not too long after we get back from winter break. Won't be immediately afterwards, but not too long after we get back from winter break. That's when we're going to be taking our next test. And as with all physics tests, you need to know everything that we've learned all year long. You need to know about vectors. You need to know about the equations of motion, the ones that I like to call the Dr. Seuss equations, all that stuff. You're going to need to know those. The majority of the questions will be focused on chapters 9, 10, and 11, but the questions will be written in such a way that you can't solve them unless you use some of the stuff from the previous chapters. So I would recommend that you spend at least a little time over the winter break going back and reviewing everything we've done all year long. Remember that tutoring is available on Tuesdays and Thursdays at 4 o'clock. And on Fridays at 11:30. And remember that we've also added 2 tutoring sessions on Saturdays now. There's one at 11 o'clock, one at 4 o'clock. So take advantage of the tutoring sessions. We have people there just waiting to help you. Now, over the winter break, we're not going to be doing tutoring sessions except for Tuesday of next week. We will do a tutoring session on Tuesday of next week. But other than that, no tutoring sessions over the break. Okay, I'm thinking that's all of the announcements. Okay, so let's go ahead and talk about last night's homework. Give me a sec to share the screen here. Okay, you should now be seeing the answers to the problems that you haven't already looked up. So 6 and 8 are ones that I need to spend at least a little bit of time talking about. But before I do that, let me just ask you to vote. So as normal, if you could only see one problem worked through from beginning to end, what would you like that problem to be? Please type it into the chat box. Okay, so I'm seeing a lot of votes for number 6, a couple votes for number 8. All right, looks like it's pretty even between 6 and 8. All right, so tell you what, I think we have enough time to do both 6 and 8. So let's do that. Okay, so number 6 was the one where we had somebody carrying a suitcase up some stairs. And I think I have enough room here. I can just go ahead and draw right on this page here. Okay, so here's where the suitcase starts out at ground level. Here's the second floor where we want to get the suitcase. And they don't tell us how many steps there are. So maybe there's a few steps, or maybe there's a lot of steps. And it turns out it doesn't matter how many steps there are. So tell you what, let's simplify it by assuming there's only one step. So if we want to get the suitcase from here to here, what we need to do is we need to take it vertically upwards, and then we need to carry it horizontally for a while. Okay, so the vertical distance that we need to carry it is 4 point something, 4.2. The horizontal distance that we need to carry it is also 4 point something, was 4.6. All right, and they tell us that the suitcase weighs 215 newtons. Now notice, they didn't say the mass was 215 kilograms. They said that it weighed 215 newtons. So if we were to do a free body diagram on the object, okay, so we've got mg going down, and then we've got the force of us as we hold the thing up, okay? And so in order for us to hold the suitcase, we have to exert a force that's equal to mg. But because they gave us the answer because they gave us the number in newtons, that means they have already multiplied it by g. They've already taken the mass and multiplied it by g. So do not take that 215 and multiply that by 9, oops, not 19. Okay, so multiply that by 9.8. Do not do that. They've already done that for you. So if some of you got the wrong answer, maybe that's the reason why. All right, so what we're going to do is we're going to break this up into two parts. We're going to calculate how much work do we have to do in this step right here. So I'm going to call that step 1. That's where we lift it up vertically. And then we move the thing horizontally in step 2. We're going to see how much work we do there. Okay, so when the suitcase is right here, the forces that are acting on it are mg going down, where mg is 215, and then the force of us carrying it up. Now, if we carry it up at constant velocity, that means these two are equal to each other. So that means the force that we're exerting is 215 newtons. And work equals force times distance, and also times the cosine of theta. But in this case, you see that the force vector is vertically upward and the displacement vector is also vertically upward. So the two of them are both pointing in the same direction. So that means that theta equals 0, and the cosine of 0, whoops, cosine of 0 is 1. So this is just 1. So it's like it's not even there. All right, so the work that we do is 215 newtons times 4.2 meters, which works out to be 903 joules. And so some of you might be saying, well, wait a minute, that's only part of the problem. That's only the vertical part. What about the horizontal part? Don't we need to add the work that we did horizontally? Well, okay, when we're carrying the thing horizontally, here, let me clean this up. Okay, so when the suitcase is located right, whoops. Okay, when the suitcase is located right here, okay, and we do our free body diagram, we've got mg going down, we got the force going up. Notice that the force vector is pointing straight up, but the displacement vector is going horizontally. So this FD cos theta, okay, that cos theta now becomes important. So let me go ahead and write it in here. Okay, FD times the cosine of theta. Theta this time is 90 degrees, and the cosine of 90 degrees equals 0. So that means this is times 0. So anything times 0 is 0. So it means the work that we do is equal to 0. So no work is done during the horizontal part of the movement. All of the work is done in the vertical part of the movement. Okay, so think of it like Atlas holding the world. Okay, if Atlas holds the world right here, if he lifts the world upward, yeah, he's doing work. But if he's holding it still, he's not doing any work. But also, if he slides sideways while holding the earth, okay, he's not doing any work then either. He only does work if he's moving it upwards or downward. Okay, so this 903 joules that we get right there, that is the total work that is done. Now, in part B, they're asking how much work is done when we carry it down the steps. Okay, so here's the steps again, but we're going to replace it with just one big step because it doesn't really matter how many steps there are. So if we've got the suitcase starts off here and ends up down here, from here over to here, no work is done there. So the only work that's done is when it goes down. So when we do the free body diagram here, so the force that we are exerting is, let me do that in a thicker arrow. So this is the force that we are exerting, but the displacement is downward. So the angle there is 180 degrees, and the cosine of 180 degrees is -1. So that means the work we do is F times D times the cosine of 180, which is times -1. So the work turns out to be negative 903. And so now some of you might say, well, negative work. What is negative work? How can work be negative? Okay. And what does it even mean to talk about negative work? Well, think of it this way. If there's a box sitting on the ground, I push on the box. So I do work on the box. I give the box some of my energy. So when that box is moving, I now have less energy than I used to because I gave some of my energy to the box. Okay. Now, what if the box is sliding towards me and I want to stop the box? So I put out my hand, and when the box reaches my hand, I push on the box. Okay. So my force is that way, the displacement is this way. So it's the exact same situation. The displacement vector and the force vector are opposite to each other. I am doing negative work on the box, which is another way of saying that the box is doing work on me. Okay, so the box is giving me energy. And what I can do is I can maybe store that energy. If I were to have a spring or something like that, so when the box hits the spring, it compresses the spring. That compressed spring has more energy than it used to have. Okay, so if you do negative work on something, what that means is that thing is doing work on you. It's giving energy to you. So when you carry that suitcase down the stairs, if you were clever, what you could do is rather than holding it with your hand, you could connect it to some sort of an electrical generator. And when gravity pulls the thing downward, then gravity is doing work. Gravity is doing positive work. And by resisting that, you're doing negative work, which means the gravity is working on you. And so if you were to connect it up to an electrical generator, you could generate electricity. Okay, the gravity is giving energy to you. And so you could generate electricity and store it in some battery somewhere. So that's what negative work is. Negative work actually does make sense. It takes a little bit of thinking before it really is going to sink in. But think about it. And I think you'll find that it makes sense. Okay, and I think we have enough time now. We can also do problem number 8. So Aurora is saying if you're ever late for a flight, you can charge your phone. Okay, yeah, I can't argue with that. Okay, problem number 8. Okay, this time we've got a bicycle that's being pushed up the hill. So again, let me draw a picture here. Okay, so here's the hill right there. I'm going to draw the bicycle as if it was just a box. They are claiming that we're pushing on the box with some force, and I like my forces to be in different colors, and I like them to be fat. Okay, so if I remember right, it was 25 newtons, but I could be wrong. Okay, yeah, 25 newtons. Okay, and then the bicycle undergoes the displacement. Let me change that to a different color here. Okay, so the displacement vector is this. The box starts out down here, ends up here. So that's my displacement vector. And the magnitude of my displacement vector is 275 meters. Okay, and the magnitude of my force vector is 25 newtons. Okay, so now notice that the force vector and the displacement vector are parallel to each other. So when I calculate my work, I get F d cosine of theta, but I don't really need the cosine theta because theta equals 0 and cosine theta is 1. So all I really need is work equals F times d. And so F is 25 newtons, d is 275. So when I multiply it out, I get the work that I did was 6,900 joules. Okay, so I don't think that anybody had any problem with that. The one that you probably had problems with is part B. And in part B, they want to know what was the work that was done by gravity. Okay, so if we do a free body diagram, the work done by gravity, well, okay, so there's mg. So the magnitude of the force vector now that we're interested in this time for part B is whatever m is times g. And they tell us what m is. What did they say? 13 kilograms. Okay. Okay, so m is 13. G is, of course, 9.8. So we can come up with a number for what that is. And so that number then goes in here for F. D stays the same, but theta now, what is theta? Well, theta is the angle in between the two of them. That's theta. So if this is 90 degrees and this angle here, I think they said was 25, right? Yep, that's 25. So theta then is going to be 90 plus 25, which is going to be 115 degrees. Okay, so what we need to do is we need to take F, which is mg, d, which is that, times the cosine of 115. And notice the cosine of 115 is going to be a negative number. If you take the cosine of any angle that's bigger than 90 degrees and less than 270, then you get a negative number. So the work turns out to be negative 15,000 joules. Okay. And so why is it negative? Well, the same reason that the work that we did on the suitcase was negative when we were going down the hill. So when we carry the suitcase up the hill, we are doing positive work. Gravity is doing negative work. When we carry it down the hill, then gravity is doing positive work and we're doing negative work. Okay. So negative work is a concept that might seem a little weird at first, but think about it for a while and you'll find that it makes sense. Okay, so that's question 6 and 8. If you have any other questions, let me ask you to hold them till the end of the class. We've got a lot of stuff we need to cover today. And so let's just go ahead and jump into that other stuff. Okay, so today we're going to finish up chapter 10. In the first part of the chapter, which we did in last night's homework, we talked about energy and work. In tonight's homework, we're going to be talking about simple machines. Now, much of this should be stuff that you've seen before. If your junior high school teacher did their job right, you should have talked about simple machines. And what you see right now are illustrations of 6 basic machines. So any kind of a complicated machine, like for instance, a clock or a robot or a car or anything like that. If you break it down to its most basic level, it's made up of a whole bunch of simple machines that are just combined together in very clever ways. So what you see right here are the machines that you should have learned about in junior high school, but you might not have, and some of you might have forgotten about them. So let's just talk about them right now real briefly. Okay, so this one here is a lever. So when you push on the handle of the lever here, you get a force on the other side that is much stronger than the force that you exerted. The lever is able to multiply your force. You got this big, if you got this big heavy box here that is so heavy that you could not lift it by yourself, well, get a lever. And this point right here, hopefully you guys remember, is called a fulcrum. You could also call it a pivot point. I've heard both terms used, so you need to know. Okay, so what you need is like a little rock or a little something that you put underneath there, and then you get a big long bar. And now, in order for a lever to be helpful, what you want is you want it much longer on the side that's closer to you than you do on the side that's closer to the thing you're trying to lift. And so the further out here that you push, the greater the multiplication factor is going to be. And so levers are things that most students understand intuitively. And so I don't think we need to spend a whole lot of time talking about the lever, other than to tell you that notice that the input force, which here they call it FE, which means the effort force. Sometimes people call it FI, which is the input force. And then this guy over here, they're calling that FR, which is the resultant force. And some people call that F0 or FO, which stands for the output force. So you're going to see those terms used interchangeably. But the important thing to note is that the input force is small, the output force is big. The lever multiplies our force and allows us to move something that we would not have been able to move otherwise. Okay, next one. This one here is a pulley. And now pulleys come in many different varieties. I have a couple of them right here. Okay, so this is just a simple pulley. So imagine that we take this part here and we hang it from the ceiling. And then this this blue ring here is the thing that I'm trying to lift up. So when I pull on this rope, it goes up. And so that is a very, very simple lever. There are also much more complicated types of levers. So this is an arrangement called a block and tackle. So if you were to look inside this thing, it's kind of hard to see, but if you look inside, you'll see there's a wheel here and there's another wheel down here. So there's two wheels inside here. And then on the bottom, there's a similar thing that also has two wheels in it. Okay, so in this case, because the rope wraps around so many times, this is going to give me a much larger multiplication than the simple lever would. And in a minute, I'm going to talk about how you can calculate that. But let's go back here to the list of the machines here. Okay, so our third one here, the one's labeled C. Okay, whoops, wrong one. Okay, I got to remember to turn on annotation before I touch my screen here. Okay, so this one here is called a wheel and axle. And the way the wheel and axle works is that you have a wheel here that you can grab the wheel and you can exert some force right here. And then the rope is attached to the thing you're trying to lift. That rope wraps around an axle up here. So when you pull, actually, this is a better place to pull, because if I pull the place that I drew it, then that's not going to work very well. The thing's going to go down, not up. Okay, so if you pull right here, okay, if the diameter of this wheel is much greater than the diameter of the axle, you will get a multiplication factor there. And so you see your effort force is really small, whereas your resultant force is really big. Okay. An inclined plane over here. Assume that you've got the box right here and you want to lift the box up to here, but the box is so heavy that you can't just lift it straight up. So what you do is you slide the box over to here. And if there's no friction, you're not doing any work when you slide it horizontally. The only work is done when you push it up the ramp. And in that case, again, because part of the weight of the block is supported by the ramp, the force that you have to push on here ends up being a whole lot less than the force would have been if you just lifted it straight up without using the ramp. So that again is a machine. So you see the theme here is that all of these machines, they multiply your force. Okay, E here, that's called a wedge. Now, some people consider a wedge just to be a special case of an inclined plane, but in your book, they list it out separately. Okay, so with the wedge, what you're doing is you're pushing downward here, and the wedge ends up exerting a horizontal force here. And this horizontal force that you get from the wedge turns out to be much greater than the downward force. And so you've multiplied your force. And then the last one here is a screw. Now, a lot of people consider a screw just to be a special case of an inclined plane. In fact, if I were to draw, let's draw the screw like this. Okay. So the threads on the screw effectively are just an inclined plane that's been wrapped around the screw there. And so in your book, I don't think they're going to talk much at all about the screw other than just let you be aware of it. It's really a special case of an inclined plane. Okay, so all of these are different types of machines. And what machines do is they multiply your force. Now, in your homework tonight, they're going to give you examples. They're going to ask you to calculate what is the force multiplier. But they're not going to call it force multiplier. They're going to call it mechanical advantage. So let me show you how this works on a couple of examples. Okay, let's suppose that here's the ground. Here's a great big heavy rock that we'd want to move, but it's so heavy that we can't lift it normally. So we decide we're going to use a lever. So what we do is we get a smaller rock and we put it right there. And then we get a big, strong bar, preferably made out of metal, but it doesn't really have to be as long as it's strong. Okay. All right. And so then if we exert a force right here, which I like to call it the input force, but your book likes to call it the effort force. So whatever. Okay. Over on this side, we're going to get a much stronger force. I like to call it the output force. Your book likes to call it the resultant force. Whatever, doesn't matter. You'll notice here the important thing is that the output force is much greater than the input force. And so what you're going to do in your homework tonight is they're going to ask you to calculate how much greater. But in order for you to do that, you're going to need to know some numbers. You're going to need to know what is the distance from the pivot point, which is also called a fulcrum. Okay. What is the distance from there to the place where you are exerting your force? So I like to call that the input distance. Your book likes to call it the effort distance. Call it whatever you want. Okay. And then you're also going to need to know the distance from the fulcrum to the place where the force gets exerted. Okay, so I like to call that the output force. Your book likes to call it the DR. Call it whatever you want. The important thing is you need to know this distance and this distance. And it turns out that the force multiplier, which by the way, okay, the book calls it the mechanical advantage. So I guess we should start calling it that too. See, so MA stands for mechanical advantage, and MA is the same thing as the force multiplier. Okay. Turns out that the force multiplier is just equal to the ratio of these two distances. So if we take the distance to the where your effort force is exerted divided by the distance to where the resultant force is exerted, that ratio will tell you what the force multiplier is, what the mechanical advantage is. Okay, pretty straightforward there with the levers anyway. With some of the others, it gets a little bit trickier, but not much. But levers are very, very simple. Okay, all you have to do is take the ratio of those two distances. Now, with levers, the real true force that you get will pretty much be the same as what we just calculated, but that won't necessarily be the case with other things. Okay, like for instance, let's look at this pulley. So let's imagine that I've got this thing attached to the ceiling. Okay, so I'm using this to lift this up. I want to know what is the force multiplier going to be for just a simple pulley, one wheel, not that multi-wheel thing. That one's much more interesting. This is really simple. So let's calculate what the force multiplier is here. Okay, so let me draw a picture. Okay, and let's get a new whiteboard here. All right, so here's the ceiling, and here's the rope hanging down, here's the pulley. This is the object that I'm trying to lift. And let me switch to a different color for the rope. Okay, so the rope comes up here, goes over the pulley, comes down. So this is where my hand is going to hold on to it. So what I'm going to do is I'm going to pull down. So this is the force of my hand pulling. And it's what your book would likes to call that the effort force. Okay, so now what's going to happen is the rope is then going to pull on the box. And so we're going to get what I like to call the output force, what your book likes to call the resultant force. And we want to know how much bigger, if any, is the resultant force going to be than the effort force. Well, with ropes, there's something that you need to understand. If I take a rope and I pull on a rope, so my right hand is pulling with 100 newtons, but my left hand doesn't want the rope to move. So my left hand is going to pull with a force that's equal to the right. Okay, so what we say this rope is under tension, and the tension is equal to whatever this hand is pulling with, which is equal to this one. So in this case, if I pull with 100 newtons, I'd say this rope has 110 newtons of tension. Now, that the tension in the rope is going to be the same. It doesn't matter whether it's here, 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 or here. Anywhere in a rope that's being stretched, the tension is the same. If I wrap the rope over a pulley, as long as that pulley is a frictionless pulley, then it's still going to be true that the tension in the rope is going to be the same anywhere in the rope. So the tension on the right side, the tension on the left side are going to be equal to each other, provided it's a frictionless pulley, which most pulleys are not. I mean, pretty much every pulley in the world has some friction, and some pulleys tend to have a lot of friction. But let's stick with the idealized case right now. Let's assume it's a perfectly frictionless pulley. So if the tension in the rope is the same everywhere, then when I go to my picture here, okay, well, I'm pulling on the rope, so that's going to cause there to be tension in the rope here, and I'm going to call that tension T. And if this is a frictionless pulley, then the tension in the rope is the same everywhere, so the tension over here is the same. So that means that the force that's pulling the box up is coming from the tension in the rope. The tension in the rope came from me pulling on it. So in this case, the output force, the resultant force, is going to be equal to the effort force, or at least the magnitudes of them are. Now the direction is going to be different because I'm pulling downward and the box is pulling upward. So the direction is different, but the magnitude is the same. Okay, so in this case, if I want to know what the mechanical advantage of it is, well, technically, it's going to be a -1. Most of the time, people just worry about the magnitude of it. So if all we're interested in is the magnitude, okay, then it's going to be a +1. But if we really want to be complete, which we should, okay, the mechanical advantage is actually going to be a -1. Okay, so basically what that means is the magnitude of this force and the magnitude of this force are the same. Now, some of you might say, well, what good is a machine if the input force and the output force, the magnitudes of them are the same? The only thing that this machine accomplished was to change the direction of the force, what good is that? Well, actually, it turns out it can be a lot of good. Okay. Imagine I've got a box on the floor here, and I want to lift that box. Okay. So have you guys heard your parents tell you that when you're lifting up somebody heavy or something heavy, you should lift with your legs, not with your back? What they mean is this. Okay, so imagine I've got that heavy box there. So I lean over this way, the wrong way, the way that your parents tell you not to do. I lean over like this, I pick up the box and I lift it up and oh, I just threw out my back. Oh, it hurts. Okay, so if instead of lifting upwards, what I were to do is to take a pulley and hook it up on the ceiling, okay? And so now I can pull downwards rather than pulling upwards, okay? I'm not going to damage my back, okay? So even though the force that I have to exert is the same when I'm using a pulley, or at least the magnitude of the force, the magnitude of the force is the same when I'm using the pulley as it is if I was just lifting the thing up. Still, the fact that it changed the direction of the force, that's a very good thing. I mean, that'll save me from throwing out my back, okay? So in that case, the mechanical advantage is a -1. Or if people aren't concerned about the direction, if all they care about is the magnitude, okay, so then they can say that the absolute value of it is 1. Okay, but now here is important. Pulleys are not frictionless, and some pulleys have a whole lot of friction. So how is that going to change things? Okay, so if the pulley has friction, then what's going to happen is the tension on the right and the tension on the left are not going to be the same. So what I'm going to have to do is I'm going to have a TR and I'm going to have a TL. And the reason they're not going to be the same is because some of the force that I'm pulling with gets, shall we say, used up in overcoming the friction. So this time, instead of being frictionless, this time we're going to say, yes, there is friction. Okay, so if I pull with 100 newtons of force, you might have maybe 10 or even 20 newtons of force. Let's just say 15 here. 15 newtons of force is required to overcome the friction. So that means that the tension on the rope on the left is only going to be 85 newtons, whereas the tension on the rope on the right is 100 newtons, okay? So you'll see that my mechanical advantage now is not as good as it would have been if it wasn't friction. So we need to have two terms. We need to have one term that talks about the ideal case where there is zero friction. And so this one that we calculated a few minutes ago, let's put an I in front of there, where the I stands for ideal. Okay, so if you have a pulley like this, the mechanical advantage ideally would be 1, or at least the magnitude of it would be 1. The actual value would be -1, but that's the ideal best possible. And so instead of calling that the MA, we're going to call that the IMA. Okay, the actual mechanical advantage is going to be less. Okay, and how do you find out what the actual mechanical advantage is? Well, remember, mechanical advantage means force multiplier. So mechanical advantage is going to be defined as the output force, which your book likes to call the resultant force, divided by the input force, which your book likes to call the effort force. Okay, so in this case, if the output force is 85 and the input force is 100, our mechanical advantage now is actually less than 1. Our mechanical advantage now is going to be 0.85. Okay, so by using this machine, it turns out that, you know, if this box really requires 100 newtons in order to lift it, what we're going to have to do, the amount of force that we're going to have to put in over here is going to be greater than 100 newtons. Okay. So in this case, we say that our machine is not 100% efficient. So this introduces a new term that you're going to need for the work tonight. E stands for efficiency. So efficiency is defined as your actual mechanical advantage. Oops, not ME, sorry, it's MA. Your actual mechanical advantage divided by your ideal mechanical advantage. Okay. So in this case, if our actual mechanical advantage is 0.85 and our ideal mechanical advantage is 1, and let's just work with the absolute value here. Let's not worry about the fact that it's actually a -1. Let's just deal in absolute values here. So the ideal mechanical advantage is 1. The actual is 0.85. Okay, and efficiencies are pretty much always expressed in percentages. So what we're going to have to do is we're going to have to multiply that by 100. So in this case, we would say our efficiency is 85%. Okay, so by using the pulley, I'm actually going to have to exert more force than I would had I just lifted the thing up normally. Okay, but I might be willing to do that because I don't want to throw out my back. Okay, so if I can exert a downward force that doesn't put me in risk at throwing out my back, then I'd be willing to do that. Okay. Now, some of you like to memorize things. So some of you are going to say, okay, if we have a simple pulley, I'll just memorize the fact that the ideal mechanical advantage is 1. Okay. Well, I got bad news for you. If I hook this thing up differently, I can get a different mechanical advantage out of it. Right now, the way I've got it hooked up is I've got it hooked up so that this part of the pulley is attached to the ceiling, and this rope right here is attached to the object that I want to lift. What if I were to do that differently? What if I change it around so that the object that I want to move, I'm going to attach this to the place where I used to have it attached to the ceiling. Okay, so I'm going to put that right here like that. Okay, and this piece here that used to be attached to the object, what I'm going to do is I'm going to attach that to the floor or the wall or something. Okay, so now what I do when I pull on the rope here, now I've got a very different situation. The mechanical advantage, the ideal mechanical advantage is not 1 anymore. I have a different mechanical advantage. And the best way to understand that is to draw a picture. So in all cases, I recommend you guys don't just memorize stuff, draw a picture. Okay, so what we've got right now is here's the pulley. And so this is the part that used to be attached to the ceiling, but I'm not going to do it this way this time. I'm going to take this and I'm going to attach this to the object that I want to move. And this side of the rope over here, actually, let me do the rope a little differently. Okay, so here's the rope in red. Okay, so this is where I used to have the object attached. Well, I'm not going to do that anymore. What I'm going to do is I'm going to take this and I'm going to attach this. Oops. Oh, I got to remember to switch to a different mode before I go touching my screen here. Okay, so the rope here, I'm going to take this and I'm going to attach it to the floor. So when I pull with my hand right here, so this is the force of my hand pulling, okay, what you're going to see is I have a different IMA now than I did before. And if you draw the picture, then you'll see what's happening. So let's assume there's no friction. Okay, so when I pull on the rope here, that's going to cause a tension in the rope. So I'm going to have a tension going this way. If there's no friction, that means the tension on the other side will be the same. So if I've got a rope here that's pulling down and a rope here that's pulling down, and these two are equal, then what force would I have to have on the upper side here in order to balance that. So this is my output force, what your book likes to call the resultant force. Can you see that what's going to happen here is this resultant force has to equal the total opposite force. So in this case, the resultant force is going to equal 2 times the tension force. And the tension force is equal to the force of my hand, okay, which is also, the book likes to call that the effort force. So you see the resultant force, or the output force, now is going to equal twice what my input force is. So this same pulley that used to give me an IMA of 1, or -1, if you want to be completely correct, it's now giving me an IMA of 2, okay? So remember, the definition of IMA is what is my output force divided by my input force. And my output force is twice my input force. So my IMA now is 2, not 1. Okay. So do not just blindly memorize stuff. What you need to do is you need to look at the situation, draw your free body diagrams, analyze the forces, think about it. Okay. And from that, you can figure out what the force multipliers are. And that's especially important if you have a fancy combination pulley like this one right here. It's got 2 wheels inside of it, and down here it's got 2 wheels inside of it. So if I were to ask you to calculate what is the IMA of this guy, okay, remember, if I'm asking for the IMA, that means I'm assuming that these are frictionless pulleys, which is actually a pretty bad assumption. Okay, but if I'm asking for the IMA, then that's what I'm after. So in this case, recognize that if it's frictionless, this is all the same rope. This is not 5 different ropes. This is all the same rope. And so if it's frictionless, the tension will be the same. So if I'm going to take this end here, if I'm going to hook this up to the object that I want to move, and this end down here, I hook it up to the ground. So I pull. So I've got 5 ropes. It's really the same rope, just 5 times. So when I pull on this and I get a tension of T, I'm actually going to have 5 identical vectors pulling down this way and only 1 vector going up this way. So this baby here is going to give me an IMA of 5. And so you just draw the pictures and think about it, okay? Now, what is the actual MA going to be? It's going to be substantially less than 5 because in reality, there's less friction here, okay? So in your book, if you get a homework question tonight where they ask you to calculate the actual mechanical advantage of a pulley like this, they would have to tell you. They would have to say something like, let's suppose that I pull with 5 or with 100 newtons on this. And when I measure the force on the other side, I'm expecting 500 because the IMA of this is 5. So I'm expecting 500, but I'm only getting, say, 470, okay? So in your homework tonight, they're going to say, all right, what does that mean about the actual mechanical advantage? And what does that mean about the efficiency, okay? So if I've got some machine here, and I don't know what's inside the machine, it's covered up so I can't see it, okay? All I know is that I am pulling this way with some effort force that they say is 100 newtons, okay? And this machine is multiplying my force somehow. And what I'm getting is I'm getting an output force that, I expected it to be 500, but it's actually only 400 and something. What did I say, 470? Okay, let's stick with that. Okay, so they're going to ask you, what is the mechanical advantage? Well, it's going to be whatever 470 divided by 100 is, which is going to work out to be 4.7. So that's my mechanical advantage. Now, if I could look inside this box, and if I could see that what was inside that box was this pulley right here, and if I count the ropes, and I find out that based on counting the ropes, I find out that the ideal mechanical advantage should be 5, okay? But my actual mechanical advantage is only 4.7. So if they were to ask you, what is the efficiency of this machine? Well, efficiency is defined as the actual mechanical advantage divided by the ideal mechanical advantage times 100, because it's always expressed in terms of percentages. Okay, so that's going to be 4.7 divided by 5 times 100. Okay, so when I punch that out, 4.7 divided by 5 times 100, and so I get 94. So the efficiency then is 94% efficient, which, by the way, most pulleys are not that good. Okay, you'd have to have a really super low friction pulley. A more typical number for a real world pulley is like maybe 70% or even 60%. If it's a really old pulley that's been sitting around for a while, so it's really rusty, it's got a lot of friction inside it. It's not uncommon to have pulleys that are only 60% efficient. But still, they're good because they will still multiply your force and allow you to do the job using less force. Okay. Now, I do need to warn you, machines don't do this for free. You have to pay a price. And let's talk about that. Let me open up a new page here. Okay, let's suppose you've got some object that's sitting on the floor and you want to pull the object here. And so there's a lot of friction. So you're going to hook up some pulleys or something, or you're going to use a machine somehow to move this, right? So the force that you need to overcome is the force of friction. And so then when you are pulling this way, this is the force of you pulling, you're overcoming friction. So you're doing work. So the work that you do is equal to the force times the distance. And if the force vector and the distance vector are parallel to each other, then we don't need to worry about cosine theta, because that's going to be 1. So for simplicity's sake, I'm going to take out the cosine theta here. Okay. So when you move a box from here to here, you have to do this work. And it doesn't matter whether you use a machine or whether you just do it all by hand. The amount of work that you have to do is the same. So if you are using a machine that allows you to do the job using less force, but the work is the same, regardless of whether you use a machine, the only way this can work out is if you exert that force over a much greater distance than you did before. Okay, so the price that you pay for using a machine is that your hand ends up moving a greater distance than it would have had you not used it. Okay, so let's see, let's go with this one here. Okay, so let's say I've got this pulley and I've got it rigged up in such a way that the ideal mechanical advantage is 2, not 1. Okay, so watch what happens. When I pull on the rope here, my hand moves down. Now you can't see very well how far it moved, okay? But if I were to measure how far my hand moved compared to how far the object moved, okay, what you're going to find is that if my hand moves a distance of 1 meter, the object only moves a half a meter. The price that I pay when I use a machine is that I have to exert a force over a greater distance than I would have had I not used the machine, because the total work is the same regardless of whether I use the machine or not. So if the machine, let's suppose the machine has a mechanical advantage, and let's assume that it's perfectly frictionless. Okay, so let's say I'm using a machine that has an IMA of 3. So that means that I can do the job using a force that is 1, oops, hang on a second here. I can do the job using a force that is 1/3 of what the force would have been had I not used the machine. But the price that I'm going to have to pay for that is that I'm going to have to exert that force over a distance that is 3 times the distance, because these two have to balance each other out, because the total work has to be the same, regardless of whether I use a machine or not. Okay. So, okay, so everybody understand that? That's the price you have to pay. And if you want to know what the IMA of a machine is, all you have to look at is the distance. See how much more does your hand move when you use a machine compared to how the hand moves when you don't use a machine. So let's go back to our simple example here. The simplest machine of all is the pulley. That's the one that's the easiest one to understand. So let me clean out a little bit of space here. Okay. So let's suppose that this distance here is 5 meters and this distance here is 1 meter. So that tells me that my IMA is 5. Okay. So when I push this handle down, my hand, if I push it all the way until it hits the ground, my hand moves that distance, but this guy only moves that distance. And what you'll find is that the distance that I have to move is 5 times the distance that this guy moves. And that's going to be true for every machine, no matter what the design of that machine is. Okay. If I'm using if I'm using a ramp here, okay, if I have a box here that I want to get up to this height right here, okay, but I push it up the ramp here, this distance here, this is how far my hand moves, so that's DE. But the effective move that I get is this distance right here, which is DR, which is the same as this right here. So if I just take the ratio of this distance divided by the effective move distance, that will tell me what my IMA is. So whenever you take the ratio of the distances, you're always going to get the IMA, and it's always the IMA. It's not the regular MA, because the regular MA is always going to be worse, because the IMA assumes that there's no friction as I push it up here. But in reality, there is going to be friction. So if I just take the ratio of the distances here, that's going to be the IMA. It is not going to be the MA. It's only going to be the IMA. Okay. So I hit you with a lot of stuff there. Are there any questions about machines and how that works that you guys want to talk about right now? I think your book does a pretty good job of describing it, but I know from past experience that unless people actually see examples, you know, like this, it sometimes is hard for people to understand. Now, this is not the only thing that you need to do for tonight's homework. There is something else that you need to do that I'll talk about in just a minute. But before I do that, let's go in and let's take a look on Canvas. Okay, there I put something on Canvas over the weekend that that will be new to you. Okay, so if we go into the modules on Canvas and we go into the extra credit opportunities, okay, there is something new in the extra credit opportunities that was not there last week. And it's in this section called Physics of Sailing. So if you click on here, then we scroll down, and the first couple ones are ones that we've seen before. This one is one that we've seen before. This next one is one that we've seen before. Okay, this is the one where I'm pulling on the rope. You know, we talked about that one before. This is the new one. This is another time when I'm out on the boat on the ocean here, and what's happening here is I've got this big old sail that you see right here, You can only see part of the sail here, but this is actually part of a really, really big sail. And you'll see I've got an arrangement here that is a set of pulleys. And the reason we need these pulleys is explained in the video, but you guys, you can guess it, because what I need to do is sometimes I need to pull on this sail with more force than is humanly possible. Okay, so I need to pull with more force than is humanly possible. So what do? Well, I use a machine. And so in the video here, it talks about how I use the pulleys. And then in this next video, it talks about another machine that is called a winch, which is very much like the wheel and axle. And so I'm not going to talk about them now because I think in the video I do an adequate job of talking about them. Now the very last one here, this is the one where if you answer the questions here, I'll give you some extra credit. In this very last one, what we're doing is we're combining the winch and the pulley together. Okay. So what's happening is I've got a winch like the one that you're seeing right here. Okay, so right. So this is the winch that's attached to the sail. And in the first part of the videos, I ask you to calculate the IMA of the pulley. Okay, but then we say, well, what if that isn't enough? So what I'm going to do then is I'm going to take this rope, and instead of me pulling on it with my hand, I'm going to take the rope and I'm going to attach the rope from the pulleys to the winch that you see right here. Okay, so what I'm doing is I'm connecting the winch and the pulley together into something that we call a compound machine, where I have two machines together, where the output of the one machine is the input to the other machine. Okay, so we call that a compound machine. And now I haven't talked about compound machines, and I'm not going to, because if I talk to you about it right now, then you won't be able to get extra credit for it. The only way you can get extra credit in this class is if you watch the video and answer the question before we talk about them in class. So it's my plan that I will talk about these in class next time we meet, which is going to be Wednesday. If you want to get extra credit for this new assignment that I just posted over the weekend, then what you need to do before Wednesday is you need to watch the videos and answer the questions. And if you do that, I'll give you some extra credit. But you got to do it before Wednesday. Okay, now, before we go, let me just tell you about two other things that you're going to need to know in tonight's homework. But I'm not going to explain them to you. I'm going to leave it to you to read it in the book. Okay. I think the book does a very good job of talking about all of these things here. So there are two concepts. One is the concept of power. And power is defined as the amount of work that you do divided by how much time it takes you to do the work. The book does a good job of describing power. So other than telling you this basic definition, I'm not going to tell you anymore. I'm just going to trust that you're going to read the book, and you'll be able to do the problems if you read the book. The other thing that you need to do is, remember how we said work equals force times distance times the cosine of theta if appropriate. What do you do if the force is not constant? How do you handle that? Well, the book tells you. And I think the book does a pretty good job of telling you. So I am purposely not going to spend any time talking about it. I'm going to leave it to you guys to read the book. And what you're going to find as the year goes on is I'm going to do this more and more often. You guys need to get in the habit of pulling knowledge out of the book, not sitting and letting the teacher spoon feed you all of the everything. That's not good. If you get in the habit of expecting the teacher to spoon feed you, that you're going to be in a sad situation when you get to college, because in college they expect you to get the majority of the information out of the book. Okay, so the only thing now is to talk about the homework, or at least tell you what the homework is. So here we go. So for tonight, I want you to do problems 9, 11, 14, and then once you get to 24, I want you to do all of the problems in between 24 and 30. Okay. So it's not that many problems, shouldn't be that big of a deal. Don't forget to take the daily quiz. That's always there too. Okay, so this is tonight's homework, problems 9, 11, 14, and then I need you to do 24 through 30, all of them. Okay. So are there any questions before I end the class? If not, you can go ahead and type bye into the chat box. And I will see you on Wednesday. If you do have a question, but you didn't want to ask because you knew it was being recorded, let me stop the recording so you can ask your question without embarrassment.